Welcome back to Chapter 3. In this chapter, we're going to be expanding what we know about our knowledge of derivatives and how to find them. So far, we have the power rule, we have the product rule and quotient rule, and those allow us to find derivatives of some things, but there are some things that it's very hard, if not impossible, to find the derivatives using that. So we are going to continue to expand. In this section, we're going to be looking at the chain rule, and we will also see how to find derivatives of parametric equations. So, our learning targets. We can use given substitutions in the chain rule to find derivatives, find velocities of objects using the chain rule. That's just find the derivative. Find derivatives using the chain rule. Same thing. Evaluate derivatives of composite functions at given values. So you find the derivative, then plug in the number. Then find equations of lines tangent to normal or parametrically defined curves. So let's start out with the chain rule. The chain rule allows us to take derivatives of composite functions. So a composite function is when we have something like f of g of x. What it says is the derivative of this, we're going to take the derivative of the outside part of the function and then multiply to the derivative of the inside part of the function. Notice the inside of this does not change. It does not change. I will be continuing to repeat that over and over and over again because that is one of the things that people mess up on the most. Also, which can be handy, is using Leibniz's notation. Y equals f of u. It's called u substitution. It gets a little bit awkward in there sometimes, but f of u and u equals g of x. So here we have f of g of x still. Dy over dx, which is the derivative, equals dy over du times du over dx. And what happens here is the du's cancel, so we end up with dy over dx. That's going to come in very handy for that parametric derivatives. So let's see how this actually works. We have f of x equals 4x squared plus 8 squared. So we have a composite function. There is an outside function and there is an inside function. When we look at this, what's the big thing going on here? The big thing going on here is that we have something squared. Something squared. If that something was just like one thing, let's say that something was u equals 4x squared plus 8, this could be written as just u squared. We know the derivative of u squared. The derivative of u squared is 2u. Except it's not just 2u. It's 2u times the derivative of u. That's kind of the, we saw this a little bit in the product and quotient rule, where we had the du's and the dv's. So it's 2u times the derivative of u. Well, what's the derivative of u? Derivative of u will be, let's see, 4x squared becomes 8x plus 8's a constant, so that goes away. So du equals 8x. Now what we do is we substitute the u and the du back in to get f prime of x equals 2 times u was the 4x squared plus 8, and then times du, which is 8x. Generally speaking, we wouldn't necessarily just leave it like that. I mean, we could easily multiply the 8x and the 2. I'm going to multiply the whole thing out. A lot of times we don't, but in this case I'm going to, because we're going to do this problem again using another method. So we have f prime of x equals, so 2 times 8x is 16x, times the 4x squared will be 64x cubed, plus 16x times 8, is going to be 128x. So that's if we multiplied it out. Again, a lot of times we're not going to do that. We'd stay with this one, or we would multiply the 8x times 2 to just get a 16x in front. But another way we could do this, in this case, is we could actually expand this. This 4x squared plus 8 squared, we could expand that because it's just a polynomial. This will be 16x to the fourth, and then we'll have 4x squared times 8 is 32x squareds, but we need 2 of those, so we need 64x squareds plus 8 times 8 is 64. And now we could just take the derivative of this using the power rule. 16 times 4 is 64. X cubed plus 64 times 2 is 128x, and then constant goes away. So I did that so that we could see that, hey, look, those two things are actually the same. We did have to go through those steps. Now, when I did this top one, I use U substitution. So it's where we take the inside, we change it into U, and then we can make the derivative of U, and we go through those steps. Now, honestly, most of the time, like, yes, that's going to happen in my head for that step, but I'm not going to write those down for simple problems like this. When the problems get more complicated, definitely you can always feel free to write that stuff down. But a lot of times, you're probably not going to need to. So, a few more problems here. So I have, I think, 5 problems on this page. Feel free to pause at any given moment and see if you can work out these problems. I'm not specifically going to tell you to, but once you start feeling a little bit comfortable, you want to give it a shot, pause, find the derivative, and then push play again, see if you're right. I will try to kind of give you the hints because each of them is a little bit different. So I'll give you the hints at the beginning, and then you can try it. So the first one, we have cosine of x squared. What's the outside function here? Like, what's the big thing going on? Well, if we have to replace something with the word something, we have cosine of something. Cosine's the big thing going on. So this is where you could pause it if you wanted to try it really quick. So our derivative here, y prime, we have cosine of something. The derivative of cosine, negative sine of that something, x squared. That is not changing. The stuff inside the trig will never change when you take the derivative. It will always stay the same. But then we need to multiply by the derivative of that something. The derivative of x squared is 2x. Generally speaking, that 2x, let's put that up front. So our derivative will be negative 2x times the sine of x squared. All right, what about this next one? Well, this looks almost the same. It's not quite the same though. The first one is cosine of x squared. This one is the cosine squared of x. A lot of times when you have like a trig function to a power, rewriting this as cosine of x squared can be handy because that means the same thing. So we have cosine of x squared. What's the big thing going on here? Again, if we have to change something to the word something, we have something squared. So that's our u. So what's the derivative of something squared? Y prime, the derivative of something squared is going to be 2 times this something. In our case, it's cosine x. Then times the derivative of that something. What's the derivative of cosine x? Is negative sine x. So the negative can go out front. Y prime is going to be negative 2 cosine x sine x or sine x, cosine x, doesn't matter. So notice in this first one, the stuff inside the trig didn't change. In the second one, the stuff inside the square didn't change. That stayed as a cosine. So again, you do not change the inside function. Our next one, we have y equals secant of 4x cubed. There's not much different with this one. This one would be a good one to pause it and try it. It's going to be very similar to that first one, y equals cosine of x squared. So I would recommend trying it on your own and then seeing what we do. So the outside function here is secant, because we have secant of something. What's the derivative of secant? The derivative of secant is secant of something tangent of something. That something is going to be the same. That does not change. And then times the derivative of the something. That'll be 3 times 4 is 12x squared. So I'd move that 12x squared to the front. So y equals 12x squared times secant of 4x cubed tangent of 4x cubed. All right, so there wasn't much different there. The big difference there was that when that trig split into two different pieces, both of them had that inside value. That doesn't change. Like one of them doesn't magically become an x or anything like that. It stays the same. So now this one, we have y equals x times sine of x cubed. Well, I said a different word there at that time that I haven't said in any of the other ones so far. Times. We have x times sine of x cubed. Well, that just means we have to do a product rule as well. That's okay. We'll a lot of times have to do product rule or quotient rule with the chain rule. Like the chain rule goes in so many things. Like you will almost always use the chain rule, it seems, just because everything has something else in it. So here, let's make u equal x, v equal sine of x cubed, which means du, the derivative of x is just 1, and dv, the derivative, so we have sine of x cubed. That's going to be like that first cosine of x squared. So outside we have sine of something. Derivative will be cosine of something. So we have cosine of x cubed times the derivative of that something. The derivative of x cubed is 3x squared. I left room to put that up front. Now product rule, we're going to multiply, and then add. So we have y prime will be x times 3x squared cosine of x cubed. Well, x times 3x squared is 3x to the third cosine x cubed, plus 1 times sine of x cubed is sine of x cubed. There we go. So we have the product rule, and then with that, we had the chain rule inside of the product rule. Well, could we have the chain rule inside the quotient rule? Sure thing, we can. So this time I came back to polynomials. We've done a few trig. The nice thing about trig right at this very moment is that it's much, much harder to expand out the trig to use what we had already known, so it kind of forces you. Like this one, yes, you could actually multiply these guys out, because I didn't choose numbers that were hugely big. But if you had, say, to the 7th power, you're not going to want to multiply that out. Like that would definitely be a time-consuming decision. So, but we can use the chain rule. So u equals 3x minus 7 squared, and v equals 5x plus 2 squared. which means du. So we'll have 2 times 3x minus 7 to the first, then times the derivative of the inside. The derivative of 3x minus 7 is just 3. So we can simplify this. In fact, let's do that. So 3 times 2 is 6. We can distribute that in. 6 times 3x is 18x. Minus 6 times 7 is 42. dv, we're going to have 2 times 5x plus 2 times the derivative of 5x plus 2, which is 5. We can distribute that, so 2 times 5 is 10. Distribute that in, so 10 times 5x is 50x. And then 10 times 2 is plus 20. So now our y prime, we're going to have that times that. So 18x minus 42 times 5x plus 2 squared minus this times this, so we have 50x plus 20 times, I'm on the edge of my screen here, 3x minus 7 squared, and then all over square the denominator, gives us 5x plus 2 to the fourth. These can simplify a little bit. For instance, there's a 5x plus 2 in each of these that could be canceled. But generally speaking, you'd have to multiply it out and simplify down and stuff like that. And that's algebra. And yes, that can be handy to be able to simplify it down, especially if you're dealing with a multiple choice question. However, at this point, we have actually completed the calculus part of the question. And so like on the AP test, if this was a free response question, this would get you full points. All that would happen between now and simplification is the possibility of making algebraic mistakes that would actually cost you points. So we can leave it like that for the moment. We have a couple more chain rule problems. So here we have sine cubed of x squared. So f prime of x equals sine cubed of x squared. So this is going to be sine of x squared cubed. So the big thing here, we've got something cubed. What's the derivative of something cubed? 3 times the something squared. So we have 3 times sine of x squared squared times the derivative of that. Well, so we have sine of x squared. What's the big thing there? Because that's another chain rule. We can chain this on. We can have as many chain rules in a row as we need until we get down to that gooey center. So we have sine of x squared. Well, that's sine of something. What's the derivative of sine of something? Cosine of something. So we have cosine of x squared. And then times the derivative of the inside of that. The inside of that was x squared. Derivative of x squared is 2x. So notice here we had the big thing cubed, got us there. And then the inside, we had something of x squared, got us there. And then the derivative of that was just 2x. We could simplify this just a little bit by multiplying that 2x in the front to get f prime of x equals 6x times sine of x squared, sine squared x squared, cosine of x squared. So notice that sine of x squared, which was the inside of the first one, didn't change. It just got a different exponent. Then the cosine of x, when we took the derivative of sine of x squared, the x squared on the inside of that one continued to stay the same. So let's look at another one. So here, the very first one we have is We have sine of something. What's the derivative of sine of something? That's right, it's cosine of something. So we'll have cosine of cosine x squared. Now that's not cosine squared of x squared, that's the cosine of the cosine. There's no shorthand or anything for that. Generally speaking, we don't see that very often in like application type problems, but they do pop up in specifically chain rule problems. So I would expect to see stuff like that. So the derivative of sine of something was cosine of something times the derivative of the something. Well, that something is cosine x squared. What's the derivative of cosine of something? Negative sine of something. And that's x squared still. And then times the derivative of that something, 2x. So we could take that negative and 2x, move it to the front. Negative 2x, then we have cosine of x squared times sine of x squared. And that would be the derivative of that one. So the chain rule we could have multiple times. In the next section, we're going to get square roots and stuff added. Later on, we'll have like exponential and logarithmic functions, and all of those will end up having chain rule in them. Well, not all of them, but most of the problems you'll do with them will have chain rule. Chain rule has to become something that is almost just like, it's almost natural. You just always chain stuff onto it. Again, one of the biggest mistakes is people trying to put the derivative of the inside back into the inside. The inside does not change. You multiply the derivative of that to the outside. Derivatives of parametric equations. So remember, a parametric equation is something like this, where you have x equals something and y equals something, where they're both of a different variable, usually t. And so what we do to find the derivatives of these is with the x equation, we could find the derivative of x with respect to t. And with the y equation, we can find the derivative of y with respect to t. Now, for our answer, though, the derivative is going to be dy over dx, because these parametric equations are still graphed on the same coordinate system, and we're looking for the slope. The slope is change of y over change of x. Well, what happens is if we take dy over dt and we divide by dx over dt, remember when you divide fractions, that would be like dy over dt times dt over dx, those cancel to get us that. So to find the derivative of a parametric equation, we find the derivative of each equation specifically, and then we divide y over x. So the derivative of secant of t, the derivative of secant is secant t tangent t, and the derivative of tangent is going to be a secant squared t. And so we can dy over dx will equal the secant squared t over secant t tangent t. And then we can simplify this. We're going to want to, because we're about to find the second derivative of this. So we definitely want to simplify. To do that, we can cancel a secant. And so we have secant t over tangent t. And then I would change them to sines and cosines. So secant t is 1 over cosine t over tangent is sine t over cosine t, which we could flip and multiply. So the cosines cancel, we end up with 1 over sine t. So the derivative, dy over dx, of this parametric function is 1 over sine t, which is cosecant t, which you wouldn't necessarily assume from x is secant t and y is tangent t to get a cosecant out of that, but that is the way it works out. So now the second derivative. For the second derivative, we are going to have to find the derivative of the derivative. But now the problem here is that, so we have to find the derivative with respect to x of the dy over dx, which is cosecant of t. And the issue there is that we don't have an x in there. We have t. It's in the wrong variable. So what we do is we will we're going to use u substitution again. We're going to take this dy over dx and make it u. So we'll end up having to find du over dx, because that would be d over dx of u. So we can do these both with respect to t, right? So we could, this is going to be du over dt over dx over dt. So this is the thought process behind it. Like, you wouldn't go through all of these steps necessarily to do it. I'll show you in the end what we come out to. So the derivative of u with respect to t, u is dy over dx. That's our first derivative. So du over dt, the derivative of cosecant t, is going to be negative cosecant t cotangent t. And the dx over dt, we actually have. We found that way over there. So our du over dx will be the du over dt, which is the negative cosecant t cotangent t, over secant t tangent t. And we're going to simplify this. Before we simplify it, what just happened? In essence, what did we just do? To find the second derivative, and this would be d squared y over dx squared. Remember, is the symbol for second derivative. So to find the second derivative, we found the derivative of the derivative that we found. We found the derivative of that divided by the dx from the very beginning. So divided by that. So it's the derivative of y prime, or it is, yeah. So the derivative of the derivative divide by the derivative of x. So that's how to do it. One of the things people find the dy over dx is cosecant t, and they're like, oh, well, so it's just the derivative of that. No, because it's not with respect to x. We have to divide by that derivative of x from the beginning. I know I'm repeating myself over and over and over here. I'm just trying to say it in different ways because it's kind of a weird idea. So, but that's what just happened. Now we can simplify. To simplify trig, change it to sines and cosines. This is going to be negative 1 over sine t, and then cosine, or cotangent, is cosine over sine. And then divide by, we have 1 over cosine. And then tangent is sine over cosine. We can flip those and multiply. So instead of being down there, they can be cosine t over 1 and cosine t over sine t. And so what we end up having is we have, let's see, 3 cosines in the top, so it's negative cosine cubed t over 3 sines in the bottom. Sine cubed t. Cosine over sine is cotangent, so this ends up being negative cotangent cubed t, which again is not something you would necessarily expect from where we started. So that's the second derivative. So the first derivative, you find the dx, you find the dy, it's just dy over dx. For the second derivative, again, it's the derivative of the derivative divided by dx. So that is how to find the derivatives parametrically. If you wanted a tangent line, that's the slope. You find the point by plugging in t. So you plug it into the slope, you plug it into the thing. And I mean, we've been finding equations of tangent lines for the past couple chapters. So with that, I will see you in class. But until then, keep working problems, keep asking questions, and as always, happy mathing.